Scientific revolutions are few and far between, but those of us who have been lucky enough to be Earth scientists in the last 30 or 40 years have seen just such a transformation in the Earth sciences called the plate tectonics theory. The central principle of plate tectonics is that convection of soft, hot rocks in the Earth's deep interior cause thin, brittle plates to move at the surface. In this lecture, I'm going to begin by setting the historic stage. I'm going to tell you about what the majority of geologists thought 40 years ago. I'm also going to tell you about the heretical and rejected hypothesis of continental drift. Then I'll set out 6 lines of evidence that led slowly but inevitably to our current view of the dynamic planet, the theory of plate tectonics. This evidence, these 6 lines of evidence, include the shape of the continents across the Atlantic, the geological features and how they match up across the Atlantic. Third, the non-uniform distribution of earthquakes and volcanoes. Fourth, the seafloor topography, especially a feature called the Mid-Atlantic Ridge. Fifth, the age of volcanic islands in the Atlantic Ocean. And finally, the phenomenon of seafloor magnetism. Eventually, the overwhelming weight of evidence convinced virtually everyone in the earth science community of this new paradigm, the theory of plate tectonics. We've seen that the Earth is a dynamic planet. It's constantly changing. It's constantly evolving. As James Hutton demonstrated 200 years ago, there are millions of years of gradual change in things like erosion, sedimentation, uplift. Even earthquakes and volcanoes can lead to dramatic transformations of the Earth's surface. We've seen how earthquakes shift rocks by just a few feet at a time, but earthquake after earthquake after earthquake can lead to many miles or hundreds of miles or even thousands of miles of movements of 2 blocks of the Earth's surface. We've seen how volcanoes add small amounts of magma in eruption after eruption, but over millions of years, those small amounts of rock end up covering 80% of the Earth's surface with volcanic rocks. We've seen that erosion, sedimentation, uplift, these are very slow, gradual processes, but once again, if you have enough time, the slowest process can cause incredible changes, transforming the entire surface of the Earth. But you have to ask yourself, what is the source of energy that drives these changes? You can't do anything without energy. You need energy. You need to apply a force over a distance to erode a mountain or to build it up. And so we have to look to the Earth for that source of energy. In this lecture, we're going to explore one of the great scientific revolutions of the 20th century, that is plate tectonics. It's a transformation in the earth sciences that took place rather swiftly in just a few short years, and also rather quietly. I think many people outside of the earth sciences didn't even know it was happening. As we'll see, the history of plate tectonics reveals a lot about the nature of the scientific method and the scientific process. I was an undergraduate in geology in the 1960s, and at that time, every textbook, every professor taught that Earth's oceans and continents are essentially permanent features. The Atlantic, the Pacific, they were always there. North America and South America, Europe, Asia, and Africa. Those are relatively constant features on the Earth's surfaces. Yes, indeed, the ocean level may have risen, inundating certain parts of the land. The ocean may have receded, causing larger, extensive lands and land bridges between the continents. But by and large, the features of the Earth had been unchanged for billions of years. Before the 1960s, there was also conventional wisdom that mountain building is essentially a vertical process. Mountains are raised up and they come down. And the principle that was described in mountain building is called isostasy. It's basically buoyancy. It's the principle of an iceberg. If you have an iceberg, you have a deep, lightweight root, and a little bit of the iceberg pops above the surface. That's the principle of a mountain. If you have a part of the crust that thickens, perhaps because of sedimentation, you have a deep root, and that whole material floats up and you get a high mountain above it. So isostasy was used to explain the existence of mountains. Also, geological processes were thought to be local and idiosyncratic. Each country, each state had its own geological survey, and instead of just matching up the boundaries and seeing the continuity, each state conducted its own sort of investigation, because gold was where you found it, rocks were where you found it, fossils were a local phenomenon. And there was no point, if you were in one state, to worry about what was going 2 or 3 states farther away. So geologists were rather localized. They were interested in particular regions of the globe. Now, earth sciences were similarly fragmented into lots of different disciplines. You had people who studied fossils, paleontologists, but they weren't particularly interested in volcanoes. And the people who studied volcanoes weren't interested in mining and economic geology, and the miners weren't interested in earthquakes. The structure of the deep interior was considered to be something totally different, and so the geophysicists, the seismologists that studied the inner structure, really had nothing whatsoever to do with the people who studied the crusts, the oceans, the atmospheres. This fragmentation was transformed, once again, by the theory of plate tectonics, as we're going to see. The theory of plate tectonics was preceded by the curious hypothesis of continental drift. This was proposed by the German meteorologist Alfred Wegener, who lived from 1880 to 1930. And he proposed this theory in 1912 on the basis of some curious phenomena he had seen in studying the geology. But it's surprising, Wegener was actually a meteorologist. He studied weather patterns, and his principal research had to do with the upper air masses of the Arctic, which seemed to drive many of the weather patterns in Europe. In fact, he died in Greenland while testing some of his theories on his 4th polar expedition. So in a sense, the continental drift theory was sort of a sideline, kind of a hobby for Wegener. Wegener's theory of continental drift was predicated on several intriguing observations, powerful observations, regarding the matchup of geological features across the Atlantic Ocean. Now, one thing you may have noticed on a globe or on a map is that the shape of the continents are rather similar. North America and South America have a coastline on the Atlantic, which is rather similar to the coastline of Europe and Africa. And he noticed this matchup and said maybe there was some reason why these two coastlines matched up so closely. In addition, he did a lot of research on specific geological and paleontological phenomena along the two coasts. And he found all sorts of intriguing coincidences of things matching up. One of the most striking, for example, if you go to a place in Wales called St. David's, you'll find giant trilobites right on the coast, right actually in the ocean surf. These trilobites of a species called Paradoxites, which occurs several places around the world, but the ones at St. David's are quite distinctive. You also find the exact same species in a very similar location right along the coast in Boston, Massachusetts. I have a specimen of a large one from Morocco of the same species, but my wife and I have collected these both in the New England area and in Wales, fragments of these trilobites that are quite distinctive and only found a few places in the world. Wegener said they match up right across the Atlantic. You also have the great diamond fields. The diamond fields in Africa, which across the Atlantic match up to the diamond fields in Brazil. There are other distinctive geological formations that match up across the ocean as well. And Wegener said this is more than just a coincidence. Indeed, he said, somehow North America and South America have drifted away from Europe and Africa. Well, the principal objection to Wegener's novel hypothesis was that it lacked any mechanism for moving an entire continent. The geological community just was not ready to abandon years of research on isostasy, on raising and lowering mountains, the vertical tectonics, and invalidate this just on the basis of a few coincidental fossils and rocks. To give you an example of the resistance, here's a quote from the distinguished American geologist Thomas C. Chamberlain. He said, quote, "Wegener's hypothesis is of the footloose type in that it takes considerable liberty with our globe and is less bound by restrictions or tied down by awkward, ugly facts than most of its rival theories. If we are to believe Wegener's hypothesis, we must forget everything which has been learned in the last 70 years and start all over again." The plate tectonics revolution resulted primarily from the merging of 6 separate lines of evidence, and indeed, geologists had to start all over again. Any one of these pieces of evidence taken alone would probably not have been enough to convince the geological community. But as in any lengthy legal proceedings, it's the eventual accumulation and weight of overwhelming evidence that swings the tide. And that's what happened with plate tectonics. By far the oldest and first observational evidence for moving continents is clearly the shape of Africa and Europe as they fit into North America and South America. You have to ask yourself the question is whether this match is purely coincidental. But early in this century, as more and more ocean soundings were taken along the coast, just off the coast of continents, it was realized that the continents actually extend out sometimes several hundred kilometers from the actual coastline, the continental shelf, and then you have a sudden drop-off into the deep ocean. And if you map the continental shelves, not just the coastline of the continents, the fit between particularly South America and Africa is much better. It's strikingly good. So that became a real question. Maybe the fit of the continents is pointing to something like continental drift. Remember, much of Wegener's geological evidence had to do with fossils and rocks that match up, and more evidence of that sort came to light. And indeed, it was sound evidence. There were very striking matchups of geological formations, rock types, mineral deposits across the coast. And that became a second kind of evidence which is very, very important in the acceptance of continental drift. Most geologists and paleontologists believe in the rocks they collect in the field. That's their first evidence. And these were specimens you could take and hold in your hand and see they almost match up like pieces of a puzzle. You have to ask yourself again, at what point do these matchups become more than just a coincidence? The third piece of evidence, the non-uniform distribution of earthquakes and volcanoes around the globe. People had long recognized that some areas are highly prone to earthquakes, some bands, particularly around the Pacific. Other regions seem particularly stable, where you never see an earthquake. Same thing's true with volcanoes. They occur in a narrow band called the Ring of Fire around the Pacific Ocean, for example. Some places you see volcanoes all the time. There are other places you'll never see a volcano. A volcano in a Kansas wheat field or in Manhattan is unthinkable. But why is that so? There must be some global control, people were starting to think, but they weren't sure what that global control was. There's a curious relationship between volcanoes and earthquakes also that began to come to light. In many regions, including Japan, the Philippines, the western coast of South America, you find strong earthquakes at the coast, and they're shallow. And as you go inland, the earthquakes get deeper and deeper and deeper as you go inland, until the earthquakes can be 100 or 200 kilometers deep. And also as you go inland 100 or 200 kilometers, you start seeing a series of volcanoes, not right at the coast, but rather inland, like Mount St. Helens, like Mount Rainier. These are mountains that are not right on the Oregon and the Washington coast, but the Cascade volcanoes are inland by 100 kilometers or more, associated also with occasional deep earthquakes. So what's this relationship? What's happening? That was a clue, but it was not yet fit into the puzzle of plate tectonics. An absolute key piece of the puzzle came shortly after World War II. That's when the Navy declassified sonar technology, which had been used to track enemy submarines. Now, you've all seen submarine movies from World War II where you have a sonar going ping, and if there's a submarine nearby, you hear the ping coming back. So ping, 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 ping. As the submarine gets closer, you hear the sonar beep coming more frequently. This is a very important technology to the Navy. When they declassified it, it became a vital technology for understanding the ocean floor. You could use sonar to bounce sound waves off the ocean bottom and measure the depth. Very simple idea, but critically important. You see, conventional wisdom in the 1950s was that the ocean bottom was an absolute flat, featureless plain called the abyssal plain. There were no features in the bottom of the ocean. We just imagine it as one vast bathtub, if you will. Well, the first sonar traverses of the Atlantic Ocean revealed an astonishing chain of mountains called the Mid-Atlantic Ridge. This chain, the longest mountain range on Earth, tens of thousands of miles long, runs the full length of the North and the South Atlantic and continues on past the tip of South America and Africa. Furthermore, it's almost exactly halfway between the two continents, and it parallels those irregular coastlines. So the Mid-Atlantic Ridge is more than just a random feature, it would seem. Splitting the Atlantic in half, paralleling the coasts, something's going on here. Can you imagine what it would have been like to discover that feature? an explorer that first finds the largest mountain range on Earth in the 1950s, if you will. 60,000 kilometers long. No longer could anyone suggest that this fit of continents was purely random. Something had to be going on. The discovery of the Mid-Atlantic Ridge and its subsequent widespread recognition was due in large measure to one person. That's the American geologist Bruce Heezen, who lived from 1924 to 1977. He was trained as a paleontologist, but he spent most of his career at Columbia documenting these ocean floor topography and preparing visually dramatic maps. And here again is a case where preparing visually dramatic material convinced people much more than any dry scientific article. By preparing a map that showed these mountain ranges in stark topography, he was able to immediately show the importance and the impact of this range of mountains. Heezen correctly recognized the Mid-Atlantic Ridge as an extensional feature, that is a place where crust is actually moving apart. But he incorrectly ascribed this extension to the fact that he thought the Earth was expanding. And as the Earth expands, the continents sort of split apart and get farther and farther apart because the Earth itself is getting larger. Following Heezen's work, similar ridges were found elsewhere in many of the oceans. There's a ridge a few hundred kilometers off the Washington and Oregon coast called the Juan de Fuca Ridge. Very important because it's very close to several universities with major oceanographic facilities. It was also documented that all of these ridges are composed of volcanic rocks, molten rocks that come to the ocean floor and are deposited along the volcanic mountain chains. So that's an intriguing fact also that you have to factor in here. Following Heezen's work, Princeton geologist Harry Hess, who lived from 1906 to 1969, contributed a seminal paper on what he called ocean floor spreading. He described these mid-ocean ridges as places where new ocean crust is formed in volcanoes and then spread laterally side to side. This is a mechanism that could have explained the opening up of the Atlantic Ocean and the fit of the continents. Then we come to the fifth line of evidence, the age of volcanic islands in the Atlantic Ocean. Now, you can use radiometric techniques. Remember, the radioisotopes like uranium, lead isotopes, and potassium argon isotopes can be used to date volcanic rocks. And if you do that, you can date the volcanic rocks from all the islands that occur in the Atlantic Ocean. Iceland, the Falkland Islands, the Canaries, the Azores, and so forth. There are quite a number of islands, actually. In 1964, a Canadian-born geologist working at Princeton University by the name of John Tuzo Wilson, he was born in 1908 and died in 1993, found a striking trend in the ages of these islands. Islands that lie close to the Mid-Atlantic Ridge are relatively young. For example, Iceland, which is right on the ridge, is still erupting, so some of those volcanic rocks are just a few years old. But islands far off the ridge are much older. The Falklands, for example, is about 100 million years old. And what he found is if you plot the distance from the Mid-Atlantic Ridge versus the age of the island, you have a very simple linear trend. The farther away from the Mid-Atlantic Ridge, the older the island. That was another important clue. Now, by far the most convincing evidence for the formation of new crust, though, came from seafloor magnetic data. This was, if you will, the smoking gun of plate tectonics. Sensitive ocean magnetometers were developed by the Navy to find submarines during World War II. And again, these were declassified in the 1950s. And they could be used to measure the orientation of magnetic minerals on the ocean floor. What you do is this. You have a magnetometer, which is just this large device which senses a magnetic field. You put it on a long cable and you drag it behind your ship close to the ocean bottom. And as you do, you can actually measure very sensitively the magnetic field that's frozen into those volcanic rocks on the ocean floor. Now, imagine what happens when a hot magma comes out of a volcano and cools. This is a hot molten rock. It contains lots of mineral grains that are gradually going to solidify and form that rock. And some of those mineral grains are a magnetic mineral called magnetite. In a sense, crystals of magnetite act like little compass needles. They actually align themselves with the Earth's magnetic field. So when the volcanic rock freezes, you freeze in the orientation of the Earth's magnetic field. It's pretty simple. But what they found was absolutely astonishing. If you dragged your magnetometer across the ocean ridge, you'd have the North Pole and the South Pole aligning with our present North Pole and South Pole very nicely. Then all of a sudden, everything would switch around 180 degrees, and suddenly what should be magnetic north was magnetic south and vice versa. The rocks were magnetized 180 degrees wrong. Now, the rocks didn't somehow pick themselves up and physically move themselves around. It was pointing to a change in the Earth's magnetic field itself. The Earth's magnetic field at times in the past has flipped. Now, we don't know exactly how this happens, but every so often, perhaps once on average every 500,000 years or so, the North and the South Pole of the Earth flip around. The Earth itself doesn't flip. The Earth is still rotating about its axis in the normal way. But the magnetic north and south, which is created by currents deep inside the Earth, sometimes those currents must flip direction through turbulence or some other thing going on deep inside the Earth. We're not really sure. But the rocks record those flips. And what they found as they sailed across the mid-ocean ridges is not only were the magnetic stripes flipping in direction, but they were absolutely symmetrically disposed, parallel to the ridge and symmetrical about it. So right at the ridge, all the rocks that were coming out today had North Pole in the right orientation. But if you moved laterally to either side of the ridge by a few miles, you'd find the orientation was wrong. And then the orientation was right if you went laterally farther out on either side. And then the orientation was wrong in parallel magnetic stripes. American oceanographer Drummond Matthews and British geophysicist Frederick Vine reported on these parallel and symmetrical stripes on either side of the ridge in the September 7th, 1963 issue of Nature. Their article was entitled Magnetic Reversals over Ocean Ridges, and that 1963 paper was a pivotal point in the history of plate tectonics. People suddenly realized here was a mechanism that showed, indeed, that new crust was being formed, moving out side to side like a conveyor belt. All these ideas were consolidated then in a very influential paper by Vine and Wilson, which appeared in Science in 1965. It presented the case for moving continents in the context of all this accumulated data. I remember in the 1960s hearing a seminar by Wilson on this subject. I was an undergraduate at MIT at the time, and the audience was rapt. Now you have to imagine, here's an audience of professors who have been teaching vertical tectonics. I've been sitting in geology classes where I learned the old conventional wisdom. Continents are fixed, oceans are fixed. Mountains are formed by being lifted up and piled down. And J. Tuzo Wilson comes into this place where professors have taught this for decades and says, that's wrong. Geology is turned on its ear. We now have a new way of thinking about geology. And I think by the end of his lecture, many of the people in the audience, even the most conservative professors, were convinced by the truth of plate tectonics. The acceptance of plate tectonics theory was swift. It was overwhelming. The few key remaining problems were quickly resolved, and it became the prevailing paradigm in just a matter of a few short years. I want to emphasize that contrary to popular opinion, scientists really are not closed-minded. They're not resistant to change. If the evidence, if the observations are there, scientists are willing to change on a dime. It has to be reproducible, convincing observations. Observations that you can make and that I can make, that we can verify independently. And then science moves forward. This is in great distinction, for example, to scientists' reluctance to at least accept as scientific evidence UFOs or paranormal behavior, parapsychology, that sort of thing. It isn't that scientists refuse to believe it's possible that those exist, but until you show us hard, concrete, reproducible data that other people can verify, it's not science. And so scientists are reluctant sometimes to comment on it or endorse it. The plate tectonics revolution, which occurred virtually overnight in terms of how many years people have been teaching other things, was different because the evidence piled up in an overwhelming sense, and anyone could see that evidence, understand its implications. Think about some of the implications of plate tectonics. If new crust is formed continuously at the mid-Atlantic ridge, where does the old crust go? We now understand that the Earth's surface is broken into about a dozen tectonic plates. These are relatively thin and brittle slabs of material. They're rock no more than a few tens of kilometers thick, but often many thousands of kilometers across. And the movement of tectonics plates is accomplished by three different kinds of plate boundaries where these dozen or so plates contact each other. Okay, first of all, you have places like the mid-Atlantic ridge. These are divergent boundaries. These are places where new crust is being formed by volcanoes. The crust moves away from both sides, laterally away from ridges of this sort. Sort of like material on a conveyor belt, but it's a conveyor belt that goes two directions at once. And that's why you get magnetic stripes that are parallel and symmetrically disposed about the ridges. Okay, then you have to have places where the crust is swallowed up. Old crust is taken back into the mantle of the Earth in places called convergent boundaries, where two plates approach each other. This process is occurring, for example, around the Pacific Rim, where you have the Ring of Fire, you have coastal earthquakes, and inland volcanoes, because as a plate approaches another, it dives underneath. You have a series of earthquakes getting progressively deeper as the plate goes underneath, and also melting fairly far inland, maybe 100 or 200 kilometers inland. That causes magma to rise and causes a series of volcanoes inland from the plate. Then you have a third kind of plate contact. This is called a transform boundary. And transform boundaries occur where two plates slide against each other. The classic example, one that everybody knows, is the San Andreas Fault in California, in which the Pacific plate is going relative north to the North American plate, which is relatively going south. And so over year after year, accumulated over millions of years, you've actually had hundreds of kilometers of movement along that plate. Now, such transform boundaries, where two plates slide against each other, are absolutely inevitable. If you have a sphere which is broken into plates, in some places new materials being formed at divergent boundaries, other places old materials being swallowed up at convergent boundaries, there have to be some places where two plates are just going to scrape against each other because of the geometry of a sphere and having these plates moving against each other. So these three kind of boundaries sort of gives us our geological action, if you will. Another key question that had to be asked is, what's the source of energy? This question that was posed to Wegener, who couldn't answer it, is exactly the same for plate tectonics theory. You have to have a source of energy. And here we can look to the Earth's inner heat. By this time, in the 1960s, it was realized that when you take rock and you pressurize it and you heat it, it no longer is brittle like it is at the surface, but it can be soft, almost like a taffy, almost a plastic-like material. And so over long periods of geological time, it can deform. It can even convect in large convection cells. And in the mantle, in the Earth's mantle, that's exactly what happens. You have convection cells where the Earth's mantle is actually, over long periods of time, over tens and hundreds of millions of years, is forming these great cycles. Well, those epic movements deep within the Earth have the effect of shunting around the plates at the Earth's surface, almost as an afterthought. So you have plate motions, the motions at the surface, everything that we think are big motions like earthquakes and volcanoes, and so forth, all that is just the tiniest afterthoughts of these epic, huge motions that are occurring down in the mantle. Well, the development of this convincing underlying mechanism for plate tectonics assured the almost universal acceptance of the field. The plate tectonics theory has tremendous power and appeal. It successfully synthesized for the first time new data from all sorts of different disciplines. Think how excited you'd be if you were a paleontologist and someone who was a seismologist or an oceanographer paid attention to you for the first time because your data actually was important to their theory. And this is what happened in plate tectonics. You had oceanographers who were for the first time showing the magnet and the topography of the ocean floor. That became a key point of evidence. Paleontologists whose fossils matching up all around the Earth in all different sorts of places suddenly made sense. You had petrologists, people who studied rocks, volcanic rocks, learning the ages of rocks, learning the distribution of rocks, and seeing the patterns there. Geomagnetists, people who were studying this sort of arcane field of the Earth's magnetic field, suddenly at the very center of the revolution. Economic geologists, because so many economic geology deposits relate to volcanoes, and since the distribution of volcanoes was now recognized as being directly related to plate tectonics, you could look for new ore deposits in places where there were ancient boundaries between plates. And whole new sets of ore deposits were discovered as a result. And so on and on and on. The theory thus integrated earth sciences as never before. The theory provided new ways of analyzing old puzzling geological data about evolution of continents and oceans, and even the evolution of life itself, because the distribution of continents affected how life distributed itself around the globe. And most important, plate tectonics theory made specific testable predictions about the Earth. Well, in summary, this lecture has introduced the overwhelming evidence that led to this startling idea that the Earth's surface is divided into thin, brittle plates, and these mobile plates are shunted about by mantle convection. I outlined 6 pieces of evidence: the shape of the continents across the Atlantic, the geological features that fit up across the continents, the non-uniform distribution of earthquakes and volcanoes, seafloor topography, particularly the mid-ocean ridge, the ages of volcanic islands, and finally seafloor magnetism. Eventually, the overwhelming weight of this evidence convinced the entire earth science community to change to this new paradigm. And so in the next lecture, we're going to explore some of the consequences of the revolutionary plate tectonics theory.